We are all apes. All of you are apes. Every single one of you. If we look in the animal kingdom, our closest living relatives are chimpanzees, bonobos, and gorillas. So here's one of my cousins. We look very different. So when did our family trees split apart from each other? What makes him a gorilla? What makes me a human? Albert the gorilla. I'm Professor Alice Roberts. Welcome to the second of this year's Royal Institution Christmas lectures. Now, Albert is going to come and say hello to some of you. He's very interested in you. I'm sure you're interested in him as well. On the surface, he looks really different, but maybe when you get a bit closer, you can see some similarities. If you hold up your hand, so he's looking right at you there in the hoodie. If you hold up your hand, he should hold up his hand as well. And you can compare your hand to his. You can see that his hand's very large, but he's got 4 fingers and a thumb. He's got fingernails. Try smiling at him. Show your teeth. He'll recognise that as a smile. He knows that you're being submissive. He's baring his teeth as well. I think he quite likes you. Do you want to say hello? Hi. Is he all right? He's harmless. He does like you. Oh, he's found a friend, a cousin and a friend. Albert, come back down here, though. Come on. Come down. Albert is a great ape. We're part of this family of great apes as well. And so those great apes include gorillas and chimpanzees and bonobos and orangutans. And then our family of great apes is part of an even bigger group of animals called primates. And all primates have various things in common. So we're all very good with our hands. We've got grasping hands. All primates have clavicles. You've got collarbones, haven't you? That's one thing that makes you a primate. And also, all primates are really, really good at climbing. Alex and Dane, that was absolutely amazing. How wonderful to see people who can use their bodies in that way and move around in 3D space like that. It reminds us just how flexible the human body really is. I think a lot of us move around in a really boring way in comparison. Which one of you here has ever tried to climb a climbing frame or a tree? You've all done it. So we are primates at heart. Thank you very much. And Alex and Dane, what an amazing performance. I thought you were absolutely brilliant. Let's ask Albert what he thinks. So what do you think, Albert, for their parkour performance? Oh, I think it was better than that. Oh, well, a big round of applause for our great apes. Alex and Dane showed us brilliantly how we can still move around in 3D space as primates do if we want to and if we train at it. But in fact, there are other clues to our primate connections. And there's one clue I'd like to show you now, which is only there for a fleeting moment in our lives when we're very, very young. So I'd like you to do a very gentle round of applause now for Vicky and Aria. Hello, Vicky.
Hello.
Hello, Aria. So Aria is very, very small. She's a very new person. How old is she?
She's 6 weeks.
She's 6 weeks?
Yes.
You're gorgeous, aren't you lovely? Now, Aria is so small that she still has a reflex that all of you will have lost long ago, but I might be able to show it to you. I want to look at her hand. Is this all right, Vicky?
Yes, of course.
And what I'm trying to do is put my finger in her hand, and she closes her fingers. She doesn't like it. Oh, no, Aria. I'm sorry, Puppet.
Okay.
Oh. She's really gripping my finger really strongly. She's got this incredible reflex, which is elicited. I'm making it happen just by slightly tickling the palm of her hand, and she grabs on. Oh, baby. So this reflex disappears by about 6 months of age, but it's something that we think is left over from our ancient primate ancestors. And Vicky and Aria, I've got a little video here to show you some cousins. So these are chimpanzees, and what you can see here is a chimpanzee baby on its mother's back, and you can see how the mum's moving pretty swiftly, and that chimp baby, even though it's tiny, has to cling on for dear life, so it's really gripping with its hands. So this is where we think this grasp reflex is left over from in our babies, but by about 6 months she'll have forgotten how to do it. Thank you so much, Vicky. Thank you,
Thanks.
Aria. Another gentle round of applause. Thank you. So we've seen now evidence of primate connections in the way that we can move with our bodies if we want to. We've seen primate connections in this amazing grasp reflex that we're all born with, but then we lose. And there are other signs of these connections when we look at anatomy. I'm an anatomist, so I go under the skin and I start looking at the structure of the body. And what I've got here are 2 bones from 2 different species. One of them is from a human, and one of them is from a chimpanzee. First of all, there's this very, very narrow groove at the top of this bone. If we look at the bottoms of the bones, there are some differences as well. So both of these bones have got a ball shape at the bottom. And on this bone, you can see that there's a much more prominent lip on it. So they're really subtle differences that tell me that this bone is the chimpanzee humerus, and this one is the human humerus. But they're kind of shockingly similar. Now we're going to put them in context and bring in 2 complete skeletons, a human skeleton and a chimpanzee skeleton. And when you look at a whole skeleton like this, I think you notice the differences more than the similarities at first, especially because the human has been hung like this, so he looks like he's walking on 2 feet. And the chimpanzee is arranged like this, so he looks like he's just getting ready to go knuckle walking, which is what chimpanzees tend to do when they drop down to the ground. So that was the humerus that we were looking at in both of these animals. That's a very similar bone in the chimp and the human. There are other bones which are much more different. So if you look at the pelvis here, that's a completely different shape. It's got a very long, flat blade, whereas our pelvis is kind of a basin shape, and it's adapted to us walking upright on 2 legs. But there are other bits that are quite similar still, and our hands are a great example of that. So if I hold up the chimp hand and the human hand, you can see that the chimp thumb is a bit weedy compared to the human thumb, but still both of those hands are capable of doing something that you can all do. Those thumbs can move in a very special way. The thumb can move right across the palm, and you can touch the tip of your thumb to your little finger. It may not feel like a really special thing to be able to do, but this opposable thumb is really important in grasping. It's something that other primates have as well, but our opposable thumbs are exceptional. So they're really great when you're making and using tools. But I want to demonstrate just how useful they are with 2 volunteers. So can I have 2 volunteers from the audience, please? So I'd like you in the mustard jumper, and yes, in the grey hoodie. Come down, come down. And we've got a little challenge for you. As you can see, it involves grapes. What's your name?
Esme.
Esme. So you're there with the green grapes, Esme. Are you right or left-handed?
I'm right.
Okay, can you put your left hand behind your back? Lovely. And what's your name?
Lena.
Lena. So Esme and Lena, you're going to be pitted against each other in a grape picking challenge. You're both right-handed, so Lena, if you put your left hand behind your back as well, so you're not tempted to use it at all. What I want you to do when I say go is pluck grapes from that bunch, just using one hand, and put the grapes in this empty bowl. So that's the challenge. All right, so taking grapes off, I'll put the bowls around that way for you as well, so it might be a bit easier. So you pluck the grapes off, you put them in the bowl, and you've got 15 seconds to do it. I'm going to give you a countdown. 1, 2, 3, 4, I declare a thumb war. Go. 15 seconds. Who's going to do better at this? I think that might be cheating. Right, stop. Stop, stop, stop. Drop the grapes. Now, the really amazing thing about this demonstration is it's meant to show how if you don't have your opposable thumb, you're much worse at plucking grapes. Do you know what, Lena? We've done it with so many people this afternoon in rehearsals, and we always ended up with a great pile of grapes over here and a very small pile of grapes over here. I think possibly you cheated by picking up the bunch and shaking it. But this does show something really important. So if you don't pick up the bunch and shake it, then you're going to end up with fewer grapes in here. Humans are also rather ingenious and very good at problem solving. So thank you very much to Lena and Esme for testing out their thumbs. Thank you. So lots of things then that we've got in common with our primate cousins: anatomy, behaviour. But actually, these similarities go down to the level of molecules inside your cells. You can actually look for similarities like this when you get down to the level of DNA. So this is when I'd like to introduce my friend, the geneticist, Professor Aoife McLysaght.
Okay, thank you so much. Well, one of the really useful things about genetics and DNA analysis is that we can actually put a number on these similarities that Alice has already been describing. So the people in row 5 all have a very special ribbon in front of you, all around there. So could you just take hold of that ribbon? And I'm going to tell you to stand up. So are you ready? Okay, can you stand up, please? And we're going to show this ribbon to everybody. Okay, great. So what you can see here across the room, that's a DNA sequence. And that's not just any old DNA sequence, that's real DNA sequence. The top ribbon is showing you DNA sequence from the human genome, and the bottom ribbon is DNA sequence from the chimpanzee genome. It's a real sequence. This actually comes from a gene called factor 9, which makes part of your blood clotting system. So the first thing you might notice when you look at these is that the top and the bottom are mostly the same. And this is what we see. The human and the chimpanzee DNA sequences are really, really similar. But there are a few differences. So I'd like the people in row 4 to help me out here. If you could just have a look, and I just want to see letter differences. So raise your hand and show me if you've got one. So yeah, we've got one up here. Thank you. So what we see here is in the human sequence on the top, we have a C and a G. And in the chimpanzee sequence on the bottom, we've got a T and an A. So we've got 2 letter differences there. And have we got somewhere else? Got a difference? Give me a wave. Yeah, over there. So yeah, so this one here, just 1 letter that's different here. So we've got a T in human and a C in chimpanzee, but the rest, they're all pretty much the same. So that's just one kind of difference that we can look at. And if we looked over the whole genome, we find that this amount of difference is actually quite representative of what we see over the whole DNA comparison. So that's about 1% different, or 99% the same, you could say. But that's just one way of counting the differences. There are actually other kind of differences. So somewhere on this ribbon, we've got a loop that's sticking out. Give me a wave if you can see the loop. Okay, over here, yeah. So in this loop here, so that's the human sequence going across the top, chimpanzee sequence across the bottom. And there's this bit that's looping out in human. There's nothing to match it against on the other side. So there's a piece of DNA that's either been inserted into the human genome or deleted from the chimpanzee genome. But we can't match those up. And there are other bits like that around the genome if we were to do the whole comparison. And that adds about another 3% different. So if we put these together, we get it's about 4% different or 96% the same. It's the kind of thing you might like to see on a T-shirt or something, don't you think? Alice, I'd like it on a T-shirt. Okay.
Okay, then.
Yeah.
We better do a countdown, hadn't we?
Okay, yeah, we should do a countdown for this.
3,
Okay.
2, 1.
Okay. So thank you so much. So the people in row 5 can sit down. Who got the T-shirts? Can we have a look at them? 99% chimp. Yeah, great. What does your one say? 96% chimp, including insertions and deletions. Very good. Who's going to wear those T-shirts? Yeah, wear them with pride. 96% chimp and proud. We made that comparison kind of easy for you. We just showed it to you. Now I'm actually going to test you on something we're not telling you in advance. So we've got some other species we want to compare. So what we have here, so Alice has a human and a chimpanzee, and I have a mouse and a rat. They're very cute, aren't they?
They're very sweet.
Yes. So I'm going to ask you to tell me which pair you think is more similar at the genetic level. So hands up if you think that human and chimpanzee are most similar at the genetic level. So good few hands. Hands up who thinks mouse and rat are most similar at the genetic level. Oh, not as many. Okay, this is interesting. So even though mouse and rat look much more similar, they're actually very similar looking, at least they are to me, they are much more different genetically than human and chimpanzee are. So we have 99% or 96% taking into consideration the insertions and deletions, but in rat and mouse, when we compare them, just the genes we can align, it's about 93%, and then there's lots and lots of those loops, so lots more that we can't compare.
These animals look very, very similar. I mean, you've got DNA here making a very similar body, little ears, little paws, little tail. These animals look much more different from each other. So that small percentage difference translates into a big difference in an actual body.
A huge difference, yeah. But what we've done now, anyway, is we've learned how to count those differences and describe those differences, but the thing we really want to know is how the genetic differences make those physical differences that you see.
Because despite the similarities, there are these big differences, aren't there? There's a big gulf between us and our closest relatives. I mean, chimpanzees don't go to school. Chimpanzees don't go to Christmas lectures. And I don't think Father Christmas even knows that chimpanzees exist. Very sad indeed. There's another big difference, and that's when chimpanzees stop climbing around in trees and come down to the ground. They don't do what we tend to do, which is walking on our 2 feet. They tend to walk on all 4s. They knuckle walk. So when did we start walking on 2 feet? In order to answer that, I'm going to need a very brave volunteer and somebody who's brilliant at balancing. Christmas jumper in the second row back, please come down. That's a fantastic jumper. Thank you very much for volunteering. You're very brave. What's your name? Stephen. Right. Now, Stephen, you can see exactly what you volunteered for. So this is a tightrope challenge. So I'd like you to go and stand on there. I'll help you get up. And before you start doing this tightrope challenge, let me just show you what I want you to start doing, because I'd like you to behave a little bit like one of your primate cousins. And we've got a little video to show you of a capuchin monkey making its way across a tightrope. So, Stephen, what I'd like you to do is bring your hands down to the cable here. Bring your hands down to the tightrope. Can you go across on all 4s? Are you going to be able to make it? Is he going to be able to do it, ladies and gentlemen? No. I'm sorry, Stephen. I don't think anybody in the audience could do it either. I don't think you can do it. There's plenty of people that are keen. We've tried it with lots of people. Nobody can do it. Nobody can get all the way from there to there. We are apes. We've got quite big bodies compared with the capuchin monkey that you just saw. He's a little tiny, small-bodied monkey. He can run along. He can keep his body weight above quite a narrow branch or even a tightrope. How would you prefer to travel across that?
Standing on 2 legs with weights on either side.
Okay, I'm not going to give you weights, but if you pop back up there, shall I give you a hand? You all right? Yeah. You can do it on 2 feet then. Have a go then. Let's be nice and quiet. Let's give him some... That's it. Yeah? Try that. I'm going to let you go now. Stephen, you all right? It's really difficult. It's really difficult, and it's also quite terrifying, even though you're only a foot or two above the ground. I'm going to do something now which I think will make it an awful lot easier for you. So, you see that rope going up? So if you walk underneath that rope and back up on the pedestal, now you can use this to help you. Don't pull on it hard and just use one hand, but I think it will give you a lot of help. So let's see how Stephen does this time. He's using the rope just to help him balance. He's not putting much weight on it at all. You can see he's weight bearing on his feet. Well done! Well done! Stephen, that was absolutely brilliant. And I now want to show you an ape doing something very similar, shot from a slightly strange angle, I must say. But let's have a look at an orangutan doing the same thing. So what that orang is doing is walking along that rope on his feet, like you walked along the tightrope, and using his hands to stabilise him. So you were doing exactly the same thing. Thank you very much. Thank you. We can do this thing of walking along a tightrope and suspending ourselves, or at least stabilising ourselves by holding on to other things. And as we've seen with the orangutan, other apes do this as well. So what we think happened deep back in our ancestry, oh, hello. What we think happened deep back in our ancestry is that our ancient tree-living ancestors were doing this, were walking around in trees, and then when they started walking on the ground more, it was quite a simple thing for them to do, to drop out of the tree and just continue walking on two legs, on 2 feet, on the ground. So we don't have to explain how you go from being a 4-legged quadrupedal animal to being an upright animal. We think our ancestors always were upright, and then they just swapped walking in the trees for walking on the ground. And then by the time we get to about 4 to 3 million years ago, we find ancestors who have started to adapt in their bodies to this new way of getting around. So their skeletons have started to change, so they're getting better and better at walking. And I want to introduce you to one of these ancestors. So this is a reconstruction of the fossil of a very, very famous fossil discovery. She's called Lucy, and she was discovered in Ethiopia. She belongs to a species called Australopithecus afarensis. Australopithecus means southern ape, and afarensis means she comes from the Afar region of Ethiopia. And this is a reconstruction of Lucy here, so we can imagine what she would have looked like in the flesh. So we can see from her skeleton that she's got adaptations to walking on 2 legs. Her pelvis has changed, it's become adapted to bipedalism, to 2-legged walking. Her femur, her thigh bone, is curving in to bring her knees and her feet underneath her centre of mass. She's still got some adaptations to climbing left in her skeleton though, including quite curved finger bones. And we're not quite sure if she was still doing a lot of climbing or whether these are just left over from her ancestors. But she's quite small. There are some other individuals from her species who are a bit bigger than her. But there's something else that's quite striking, I think, about her limb proportions. She's got longish arms and short legs, so she doesn't really look like us yet. And there's a change to long legs that happens about 2 million years ago, with a new species appearing. And this species is called Homo erectus. And Homo erectus appears about 2 million years ago. This particular reconstruction is based on a fossil from 1.5 million years ago, and he's called Nariokatomi boy, because his fossilised remains were found near the Nariokatomi River in Kenya. And he's quite interesting when you look at his bones, because he looks like he's 15. Have we got any 15-year-olds in the audience tonight? If I were to do an X-ray and look at your bones, I'd see that some of your bones still had gaps at the ends. They haven't fused yet because you're still growing. And his skeleton looks a bit like that, but you're nearly fully grown. So he's got the skeleton of a 15-year-old, almost fully grown. But then if we look carefully at his bones and his teeth, it turns out that he was only 8. So he's only 8, but with the body of a 15-year-old. He grew up really, really fast. He didn't have the long childhoods that we have, and those childhoods are really important. important to us as humans. They allow us time to learn before we grow up into adults. We can see other things in his skeleton. In his back here, he's got strong back muscles, and then moving down to his legs, he's got strong leg muscles, and he's got really springy tendons, particularly this one here, the Achilles tendon that attaches at the heel. We can see from the bones that he had a really lovely, big, springy Achilles tendon, and that's why we've reconstructed him like this, because we think Narikatomi boy was a runner. But in order to see just how good the human body is at running, we're going to look at it in action, and Aoife's in the library with a runner.
Hi Alice, yeah, I'm here in the library and I'm with Marcus from Sheffield Hallam University and also our very wonderful volunteer Tom, who's been running here on the treadmill for quite a few minutes. So Marcus, you've been capturing his movements.
Yeah, exactly. So you might see that Tom's covered in all of these spherical markers. And what we can do, we can use these motion capture cameras that you can see dotted around in the red cameras, and they can really accurately measure the position of those markers.
Yeah, and we see his head is staying quite steady, and we also see that his shoulders are moving back and forth.
So motion capture is a technology which people like Marcus, who are sports scientists, can use to analyse how the human body moves, but also to help athletes improve their performance. And we can see, looking at that little stick man there of Tom, his shoulders are moving. So by the point in time we've got Narikatomi boy, we've got a nice long waist, and that enables your shoulders to rotate, and that helps you to balance, and it makes running more efficient. And we've also got his head staying quite still, so like Narikatomi boy, he's got nice strong muscles and that strong ligament in the back of the head, and strong back muscles to stop his body pitching forward. Because actually when you're running, you're pretty much falling over almost at every step, and you've got to stop yourself doing that. So we're seeing those adaptations in action, but actually there's something else that would stop you in your tracks with running. And I think, Aoife, you're measuring that as well.
Yeah, so Tom is a pretty wonderful volunteer because he has also swallowed one of these. This is a really small thermometer, and he was asked to do this by Dr. Danny Longman from Cambridge University, who's also joining us here. So what have you been measuring?
Sure, so the pill that Tom swallowed earlier is transmitting data wirelessly to this laptop here. And that's giving us information about Tom's deep core body temperature, letting us know how warm he really is.
And what do you see here? So we've got a graph of his temperature.
We do indeed.
Yeah.
So we see here at rest, Tom had a core body temperature of 37 degrees, which is that of a healthy human. However, when he started to run, about here, we see that his core body temperature started to rise, and that was because his muscles were activated, and muscle activation generates a lot of heat.
He looks quite hot.
He does indeed.
Yeah.
So when Tom started to warm up, his evolved heat loss mechanisms began to kick in, and he was able to lose heat at the same rate as his muscles were producing them. And we can see here we actually get a plateau in core body temperature.
Yeah, and is this the same then for other animals?
Well, if we were to have a gazelle or a cheetah doing this experiment in place of Tom, we would see that the core body temperature would continue to increase. They don't have the mechanisms to lose heat that we do.
So a cheetah would have to stop despite being so fast.
Absolutely.
Yeah, yeah. So Tom here is better than a tomcat.
So there's obviously something that our bodies are doing in order to regulate that temperature and to try to keep us cool, whilst everything we're doing is trying to make us hotter and hotter and hotter. And the amazing thing about being able to regulate our temperature like this is it means we can just carry on running. We're really good at endurance running. We can even outrun horses and dogs. And there's a particular secret to how we do it.
That was
and
good,
Aoife,
wasn't it?
you happen to be back
Oh, yeah?
in the theatre.
Uh-huh.
So you're going to demonstrate for me, Aoife,
Yeah.
what our superpower is, how
Okay.
we managed to keep our temperature
Okay. Yeah.
down. There's a spike.
Uh-huh. And we've got these balloons.
And we've got these balloons. So this balloon represents the amount of sweat that a 70-kilogram dog sweats out during an hour of exercise.
70 kilograms is bigger than me.
Yeah, it's
Yeah,
quite a big
that's a big dog.
Yeah, I'm going to go and stand over here.
Okay, you're making me worried, Alice. I'm wearing my good shoes. Okay. Well, I need a countdown. I'm not doing this by myself, okay?
3, 2, 1.
Okay.
Okay, so
It
that
wasn't
was...
as bad as I expected, so that's
No,
a
it's not
70
too bad,
kilogram.
is it? That was a 70-kilogram dog. Dogs don't sweat that much. They have to stop, and they have to bring their temperature down by panting.
Okay.
But humans sweat quite a bit. So this balloon contains the amount of sweat that a human sweats out
Okay.
during an hour of exercise. So we probably need a countdown again. 3, 2, 1. That was 2 litres.
Oh, yeah.
2 litres of sweat.
I think I felt it, yeah.
Are you a bit wet?
I'm a bit wet.
I'm
now,
sorry,
yeah.
Aoife.
You're not really sorry, though, are you?
Not really, no. Not really. So Aoife has magnificently, I'm so sorry, Aoife. She's going to get me back now in lecture 3, isn't she? She's going to be thinking of something to do to me. Aoife's demonstrated brilliantly, I thought, absolutely brilliantly, the secret of sweat. This is how we humans manage to keep our temperature down. And there's something about us that's very, very different from our closest living ape relatives, and that is, it looks as though we've lost the fur over our bodies. In fact, that's not quite true, because over the surface of the human body, we've got 5 million hair follicles, and that's actually the same as a chimpanzee has. It's just that our hairs are so much finer over our bodies. And that's really important, because it means those hairs don't trap sweat. The sweat spreads out on the surface of the skin, and then it can evaporate off. And as it evaporates off, it takes heat with it. So we're really, really good at sweating. And so we're able to run long distances. And we think this was incredibly important to our ancient ancestors, people like Narikatomi Boy. So going back 2 million years ago, we've got the expansion of grasslands in Africa, savanna. And with the expansion of those grasslands, we've got the expansion of populations of animals who are eating that grass, so grazers. And then the predators are eating the grazers. And if you could run fast and get to a carcass that a predator had taken down, perhaps those lions have gone off to sleep in the shade, you can steal some of that meat. So our ancestors were certainly scavenging, they may have been hunting as well. And we also know that they were making stone tools that can cut through flesh and sinew. And now I want to introduce to you 2 people who make stone tools today, and they make stone tools that are very much like those of our ancestors, Anthony and Nada from the Ancient Technology Centre in Dorset. Let's give them a round of applause. Now, before they get started, some very sharp flakes can fly from this, so I'm going to put goggles on. And those of you in the front row have got goggles. I think, yeah, front and second row. We may get some flakes flying off, so let's just be careful about it. So Anthony and Nada are going to start making stone tools, and they do it by bashing rocks together. It's actually quite complicated, isn't it? I've had a go at doing it, and it is difficult to do it.
It's quite a lot to it. Yeah,
go on then, Anthony. Bash a couple of flakes off, and let's see what happens. And he's using a cobble to break those flakes off. Oh, that's amazing. Look at that. As soon as you do this, as soon as you start breaking flakes off, you end up with things that have got very sharp edges. It's a cutting edge. I mean, this is a stone knife. Absolutely brilliant. So you can actually see how thin that flake is just there, especially if I shine a light through it. You should be able to see quite nicely that it's incredibly thin at the edges. That's a really, really sharp cutting edge. So you'd be able to cut up your Christmas turkey with that very easily indeed. Thank you. So Anthony's making fairly basic flake tools. And over here, Nada is making something a little bit more sophisticated, the kind of tool that Narikatomi Boy might have made, actually. Nada, would you mind holding it up?
Not at all.
So this is a hand axe. She's making flakes which are useful as knives, but this is useful too, isn't it?
Yes, absolutely, yes.
Yeah.
It's a multi-purpose tool.
Yeah, so you could use it for chopping, maybe, smashing bones to get marrow out, or...
Absolutely, yes.
Yeah, all sorts of things. The other really interesting thing about this particular shape is it's a shape that gets copied and copied and copied and passed on down through the generations. And that I think this tells us something really important about the minds of these tool makers, because it's not just simply a question of bashing away at it, is it? You've got a shape in your mind.
No, you have to visualise what you want to get out of a rock and work towards that shape, absolutely.
Yeah, so you are like a sculptor. You're making the shape. So that means our ancestors, even as long ago as Narikatomi Boy, were capable of abstract thought like this. They could hold the idea of a shape in their heads. It's quite a special thing to be able to do. And not only that, they could make it real, which is even more special. Thank you ever so much, Nada and Anthony. That was brilliant. Thank you. Now, stone tools tend to stick around in the archaeological record. They're the kinds of things that archaeologists can easily find and dig up. They're, after all, stone. It doesn't really rot away. Things we don't find so often in archaeology are made of organic materials. So anything made out of leaves or grass or wood is usually going to rot away. And so it's very difficult to know exactly what our ancestors were using in terms of wooden tools at this point in time. But we do know that lots of hunter-gatherers use very simple wooden tools like this. And you can imagine making this, just taking a stick and then using one of those stone flakes to sharpen the end of it until you get a point. And then perhaps what you're thinking is, I'm going to use that as a spear. Well, I could, but actually you can use it for something else as well, something very important. And lots of modern-day hunter-gatherers use sticks like this to dig food out of the ground. And there's a really important clue as to what that underground food might be when we delve into genetics.
That sounds like my part. Yeah, so we can actually learn something very interesting about our adaptations by looking at our genes. So in your mouth, you have spit, of course, and in your saliva, there is an enzyme called amylase that helps you digest starch in your mouth, start breaking down the starch in your mouth. And the amount of amylase you have in your saliva depends on your genes. So all of you will have noticed that you have a little packet of crackers. So you can get your packet of crackers out. Yeah, so you're not to start eating them yet because I need to tell you what to do first, but you can just quickly take them out of the wrapper. Okay, what I want you to do is I want you to start chewing the cracker, but you're not to swallow it, okay? You have to keep it in your mouth and keep chewing. It's going to get, not yet. It's going to get all mushy and it's going to get all gooey and whatever, but that's fine. Just keep it in your mouth and keep chewing. And at some point, the flavor is going to change. So when the flavor changes, I want you to stand up, okay? So is everybody ready? Steady, go. Just chew. Don't swallow it. And then let me know when the flavor changes. Oh, we got one already. Very good. Now, yeah. More. And this is totally normal. It's actually expected that different people stand up at different times. So this is amazing. Everybody's starting to stand up. So, I'm running around the stairs. What was the flavor change for you?
Boring.
Boring, okay. It changed to boring. Did it start out interesting? What did you think?
Sweet.
It changed to sweet. What did you think?
Sweet.
Interesting. This is very good. What did you think? Did it change for you? It got sweeter. It's interesting that we have people saying sweet because that's what I expected. So the amylase enzyme in your saliva, what it does is it breaks the starch down into simple sugars. So it's what we expect, is that it starts to feel sweet for you. And the reason different people stood up at different times is because actually we know that humans have different numbers of copies of this gene that makes the amylase. So some people have 2 copies, but some people have as many as 18 copies of this gene. So if you have more copies of the gene, we expect that the flavor would change to sweet sooner. And in parts of the world where there's a traditional diet that's very starch-rich, so things like rice and potatoes and yams, we see that people who come from that part of the world tend to have more copies of the amylase gene. So it's an adaptation to diet that's written in our genes.
Yes, but our ancient ancestors also had another way of unlocking the energy from their food. Woo! By 1 million years ago, our ancestors had controlled fire. And with fire, they could do all sorts of things. They could obviously keep themselves warm, they could ward off predators, and they could do something really important when it came to food. They could cook it. So things start to taste a bit nicer, perhaps. But even more importantly, if you can cook food, then it means you're doing some of the work in unlocking the energy from that food before you get anywhere near your mouth. So you're effectively getting more energy from your food. And we think that this is reflected in a change in our ancestors' anatomy. So over time, what happened is that our ancestors, thank you very much, who started off with teeth as big as this, huge gnashes, over time, those teeth diminished in size and got a lot more like the teeth in your mouth. So modern human teeth are tiny in comparison to this Australopithecine jaw with its teeth. So if you can make your food softer You could do that by pounding it. You could do it by cooking it. It means there's no longer any advantage in having great big teeth like this, and your teeth can grow smaller. And then something else that happens is that brains are getting larger. And if I compare these two skulls by showing you the skulls like that, you can see that this modern human skull is much bigger compared with this one. The brain cavity, especially at the front, just above the eyes, is much, much bigger. Now, the brain is a really important organ, and making a change to a brain is something that's quite difficult to do, as we can see from genetics.
Yes, we do. And so there's something really, really amazing that we can do with DNA sequence analysis, which allows us to actually figure out which are the important genes. And so to explain this to you, I'm going to tell you a story. And this is a true story, and it takes place in World War II. So the Air Force wanted to reinforce their planes. So they had this idea that they would reinforce the parts of the planes that get lots of bullet holes. So they brought in a statistician to help them. They wanted him to count the bullet holes and figure out where they are. But in order to picture this and to figure out what kind of challenge this was, we're going to do something. So you all have paper aeroplanes under your seat. So just take them, don't do anything with them yet. Okay? So if you just take a quick look at those, you'll see that you have holes punched in them. So that's like a bullet hole. And so what I want you to do, when I give you the word, don't anybody go early, I want you to throw those airplanes, and I want you to aim for me. Not yet, please. I want you to aim for me, because basically I'm on home base, okay? Are you ready? Steady? Go! Well, that worked. Okay, so the job the statistician had then, these are all the planes that made it back to home base, and he wanted to look at these. So I need to keep track of what's happening. Okay, I'll mark them on this. Alice, you could give me a little hand here. So this one has a bullet hole there, so you can take that from me.
Yeah.
And what I'm going to do is I'm going to make little marks on this plane. So there's one there.
Yeah, there's one on the wing.
One on that little bit of the wing.
Yeah. There's one on
the
that
other
bit of wing.
Okay, this is going to take forever. We need a bigger plane. Thank you. Okay, so this plane, we've already collected all these data. So this is what this statistician had to do. He had to collect the information from all the different planes that came back, and he mapped them onto a picture of the plane. And the legend is that the Air Force's first instinct was, well, we're going to patch up those bits of the plane that have loads of bullet holes in them. But the statistician said to them, no, you've got it wrong, really, because actually we noticed these parts of the plane that have no bullet holes in them. So what's happening there? Well, they're the planes that didn't come home. They're the ones that had a really bad damage they couldn't fly with. These are the bullet holes that allowed the plane to fly despite the damage. So these parts of the plane are things like the engine, or the cockpit, or the steering gear. So by looking at the pattern of bullet holes, you can see the important parts and the less important parts. And it turns out we can do this same kind of analysis with gene sequences. So if you imagine for a moment that this is a genome, then we have some genes in the genome where lots of mutations happen. So the DNA changes, but it doesn't really matter. So there's a change, but it's not a significant change. And then there are other parts of the genome, other genes, that they really matter. And when you get a change in them, it really affects the individual. So they can't survive and thrive as well. And if we look across mammals and we say, well, which are the genes in these really important areas, we find that there's especially, in these parts of the genome, it's especially genes that are involved in your brain. So genes that work in your brain. But something really changed in human evolution. Whew. So in early human evolution, these brain genes started changing quicker. They started evolving faster. So this is a really unusual pattern. And this tells us that something was driving that change. Something really important had happened.
So in order for those mutations to start appearing and then building up and creating this big difference in brains and getting brains to grow larger, there must have been a significant advantage in growing a bigger brain. And anthropologists have racked their brains about what that could possibly be that was driving this increase in brain size in human evolution. They said, well, our ancestors must have been working together in teams on the African plains as hunters. So maybe it's cooperative hunting. Maybe that's what's driving this increase in brain size. But then hunting dogs and lions are great at cooperating in hunting, and their brains aren't very big at all. So then anthropologists said, well, maybe there's something else. Maybe it's stone tools. Maybe you need a really big brain in order to be able to make stone tools. But actually, that turns out not to be likely either, because our ancestors started making stone tools more than 3 million years ago, when again, their brains were pretty small. There's another group of anthropologists who think they've got a hypothesis which stacks up when it comes to brain size. And I need a volunteer now to help me explore that hypothesis. I'm particularly drawn by Christmas jumpers, so I'm going to pick you with a fantastic reindeer Christmas jumper. Come on down. Jasmine. Right, OK, I've got a bit of a challenge here for you, Jasmine. What we've got here are some cubes. And the cubes represent brain size. In fact, they represent a very special bit of the brain. They represent the grey matter on the outside that we call the neocortex. And we've scaled it to body size. So this must be an animal with a very small amount of neocortex, and then this must be an animal with a large amount of neocortex. Underneath these cubes that represent that different brain size, we've got a clue as to what it is that's driving brain size increases or explaining brain size increases. So what I'd like you to do is lift up each of these cubes and we'll reveal a score for each species. Here we go then. What's the score for this one? The score is 1. And this species is a slow loris, a very cute type of primate. OK, what about this species here? Let's reveal a score for this one. Oh, that's a lot. That's 17. I can count very quickly. Small cubes. And this species is a spider monkey. What about this one? What's the score for that one? Oh, 54 small cubes. This one is a chimpanzee. And then finally, would you like to lift that big cube? There's a pile of people underneath it. This is a human. And what these scores represent, Jasmine, is the size of social group that these animals normally live in. So the slow loris is a very solitary creature. It doesn't have any friends. It just lives on its own. Spider monkeys are a little bit more gregarious. They live in a social group which averages 17. Chimpanzees, even more, average group size of 54. Humans, on average, we have 150 friends. And that's not just acquaintances, that's people we know pretty well. Jasmine, thank you for revealing the secret of big human brains. Thank you very much. So it turns out then that it's most likely that our big brains are all about making friends and keeping friends, making those connections. After all, we are quite puny apes, and we've done ever so well for ourselves as a species. And we've managed to expand across the whole world. And what we're going to do now is map out those expansions. And I need 2 volunteers to come and help me colonise the world. There's somebody in a blue T-shirt, on second row to the back. Yes, you. So come down. Aoife, have you got a volunteer your side?
Yes.
Hello. I've got Tessa here.
Down. Yeah,
come on down. Come on down. Wonderful. Just come here. Turn around. So what's your name? Shireen, lovely to meet you. OK, so Tessa and Shireen, what we're going to ask you to do is start in Africa, because that's where our species starts. So can you find Africa on the map? Go and plant your feet on it, occupy it. That's where our species starts. And our species originated in Africa about 300,000 years ago. So you can each put a pair of feet firmly on Africa. Now, we might need to reload these as we go.
We might.
OK.
Yep. So
you start in Africa, plant them on the map. You can walk around in Africa a bit. You're all over Africa. So our species was just an African species for a few 100,000 years. Then about 100,000 years ago, Tessa, if I move you backwards, you can start to come out of Africa, make a little trail of footprints. And you can come all the way along here into Asia. Do you need a bit more paint? And you can come along here
through South Asia. Do you want to come all the way down into Australia? By 65,000 years ago, modern humans had reached Australia.
Yay.
Fantastic. I'll move you back over here. And now, Shireen, if you are you nicely loaded up with paint?
Yeah.
You can start making your way into Europe if you like. So from about 50,000 years ago, and you can walk all the way over to Britain. Can you see Britain on the map? By 40,000 years ago, modern humans, Homo sapiens like us, had reached Britain. Lovely.
Yes.
Very nice. Tessa, I've got a bit more work for you to do. Start from here in South Asia, and then you can walk all the way up to the north, up to the coast of the Arctic Ocean by 30,000 years ago. Come over here, you can walk across here. Actually, there's a land bridge here because the sea level's low, and you can pop across into Alaska. And now the ice is melting in Alaska, and you can walk all the way down to South America. We've colonised North America. That's the Clovis hunters of North America. And we've got people going all the way down into South America. We have colonised the world.
Yay!
Fantastic. Well done, Shireen. Brilliant handiwork, I think, there, Shireen and Tessa, or I should say footwork. We've colonised the globe. Good work. Thank you very much.
Done.
Thank you. It took a while to get into Europe, didn't it?
It did. There was a little bit of hanging around. I think they might have met some friends around here.
Oh, indigenous European people.
Well, these earlier humans who were already there before the modern humans got there.
Yeah, yeah.
Neanderthals.
So the Neanderthals were the inhabitants of Europe before our lot got there. And we used to think they were entirely separate. Looking at their bones, we thought that there was never any kind of real interaction between modern humans and Neanderthals. But genetics has changed all that.
So what we can do now, we can actually get DNA out of these really old bones. So we've been able to get DNA out of Neanderthal bones. And this revealed some really interesting surprises, because when we looked at the Neanderthal DNA, you could see that it didn't look actually totally different from human DNA. So as you know, you got half your DNA from your mom and half from your dad, right? So 50-50. And then you've got about 25% of your DNA from each of your grandparents, and then different amounts from other ancestors. And when we look at people today, we find we have chunks of DNA that are from a Neanderthal ancestor.
I've got a bit in my genome.
Yeah, me too.
Yeah,
And
we
there's
all
only one
have.
way to get a chunk of DNA from somebody else.
Yeah, shenanigans. Something went on. There was some serious interaction between modern humans and Neanderthals.
You're shocking the parents.
And it's not just Neanderthals.
No.
There's this other species who are around over here in Asia, and we met up with them as well. We don't, well, they may be a species, they may just be a different, slightly different set of people. They're called the Denisovans.
Yeah, my view is that they're the same species. We're all the same species because of all this mixing.
Do you think?
Yeah.
That's something we disagree on.
That is
I
something
say
we
for the
disagree
bones,
on.
Neanderthals are a different species, but genetically you're saying they're the same.
The same.
See, scientists don't always agree.
No. But with the Denisovan, there's so little you can say anyway. There's so little in terms of bones.
A finger bone and 3 teeth, I think.
But when we can get really good DNA, actually, even though it's just a tiny bone, the DNA inside it was really, really well preserved. And so it's really good DNA sequence. And if we look at people, especially people from around this part of the world, we see that they have chunks of DNA from Denisovans.
But we've got quite a lot of Neanderthal DNA hanging around, haven't we?
Yeah, yeah. So we all have chunks of Neanderthal DNA, but we have different chunks of DNA. So if I was to take all the different chunks and tile them together, we get about 70% of the Neanderthal genome is in people walking around today.
I can do better than that, Aoife.
Can you?
I can show you a whole Neanderthal. So with the help of some quite amazing prosthetics, we have transformed a modern human into an ancient Neanderthal. And we can see that there are differences in the face shape. She's got a very big brow ridge compared with us modern humans. And actually she has a lump at the back of her skull as well, which you can't see under all this hair. But the skull shape's also a different shape to ours too, a bit long and low compared with our more globular face shapes or head shapes. She's got a very chunky jaw, but actually, she looks similar enough to us that I don't think you'd really notice if she was walking down the street, would you? And we keep on finding more clues that Neanderthals were more like modern humans than we thought. And one of those clues is in what she's holding in her hand. So this is a shell, and it's a replica based on one that was dug out of a cave in Spain. And it's a scallop shell that's been pierced, so perhaps used as a pendant, and also painted with red ochre. So it seems that Neanderthals were interested in decoration and art in the way that we know our own modern human ancestors were as well. So perhaps a lot similar to us than we previously expected. Anthropologists for a long time have wondered whether Neanderthals had language like we do. And that's something we may not ever know. I mean, can you speak?
Of course I can speak.
We've solved the riddle. Thank you. Although Neanderthals have left a little bit of themselves behind and still alive in the form of fragments of their DNA in our genomes, as a group of people, they had died out by 20,000 years ago. We don't find their fossils anymore. But modern humans survived through the peak of the last ice age when the ice sheets descended over northern Europe and over North America. And it's at this particular time that we see an amazing explosion in art. We see our ancestors making fantastic sculptures out of bone and ivory, and they also painted the caves that they lived in. And here's a wonderful painting of an ancient human in a cave painting some of the animals that are in her environment. And there's a child holding a lamp there, which has probably got some animal fat in it, burning away so that she can see what she's doing. And you might think that this seems really frivolous, that these are people surviving through the depths of the Ice Age. And shouldn't they be out hunting and gathering and keeping their families alive? You know, what are they doing painting caves and making art? But it's not frivolous. Art is a really important part of the way that we communicate with each other. And this really underpins our success as a species. We carry on expanding, we carry on making culture.
And what we see from the genetics is that throughout our history, we've been moving and mixing with archaic humans and with modern humans. And we see this continuing today. The ethnic groups and the populations that we recognize today are just a mix of lots and lots of people.
In the third lecture, we're going to look at human diversity today, and we're going to find out how those ancient migrations contributed to the patterns that we see around us today.
And we're going to look at how our DNA influences who we are.
But for now, we're going to close this lecture with a celebration of all of our ancient hominin ancestors, everything that they've given us, our love of art, our language, all of those secrets and gifts tucked away in our DNA. And we're going to celebrate them all with a little musical number.
Ta-da! You can help me here, Alice.
Really?
Yeah. You can. I'll just leave you in charge of one, okay? Everybody ready? See if you recognize this.
Lectures have been filmed for 82 years, but a few are missing from the Royal Institution archives. If you think you might have any recordings hidden away in your attic, please dig them out and let us know. The missing lectures are listed on the Royal Institution website. Thank you.